Now we have all the building blocks together to code the GPT model architecture. Before we jump into the code, let me just show you a visual showing you the whole GPT model architecture in one figure. So here what you can see is the GPT model architecture, and there are of course familiar parts to it. The input text that is tokenized and then embedded with the token embedding layers and the positional embedding layer. And then we have an optional dropout. And in the center here, the box here, that is the transformer block that we have just implemented in the previous section. And you can see it's repeated 12 times. Why 12? That's a design decision. You as the designer, you can choose this number. But I'm using 12 here because that's what the original GPT team used for their smallest model. But I will also show you later that we can change this number and have differently sized GPT models. And in the transformer block, you see all the familiar parts that we implemented in the previous section. Then we have a layer norm and an output layer. Now, what's interesting is that the output layer doesn't output words, it's outputting numbers. So what do these numbers mean? If you pay close attention, you might see that there are 4 input tokens and there are 4 rows here. So each row here corresponds to one of the input tokens. However, instead of being a word, you can see this is a vector here. So each token is represented by a vector, and this vector is 50,257 dimensional. Where do these dimensions come from? So here in the input layer, what we do is we convert a token ID that corresponds to 50,257 entry vocabulary into an embedding vector. So we go from this huge vocabulary space into an embedding space. And here at the output layer, we go back from an embedding space into the vocabulary space. So there is one more thing that we have to do to convert these vectors back into words, but we will leave that part for the next section. Here, we're just focused on coding the architecture itself. So yeah, let's jump in and let's get working here on the architecture. And because I'm lazy, or maybe because I thought it all through, depends on how you want to think of me, I will just copy and paste this dummy GPT model class that we implemented earlier. So let me just copy and paste this to make my life here a bit easier. So yeah, I'm copy and pasting it here. And then what we can do is we can replace all the dummy parts, because now we are going to implement the real architecture. We can just delete those. We get rid of placeholder because it's no longer a placeholder, because our dummy transformer block is now the real transformer block. And then I can do the same thing here for the layer norm. And if I see it correctly, we don't have any other placeholders here anymore. So this one should be the working GPT model architecture. We can actually try it out. So let me initialize a random seed here so you get the same results I do. And then we can instantiate the model. So I'm going to initialize it with the configuration file we had earlier at the beginning of this chapter. And let's actually use some real data now. So we had somewhere real data. Let me scroll up a bit here. So here we defined batch as 2 inputs, input text that were embedded into token embeddings. Let me just copy and paste here so that we can make sure this actually still works. So yeah, we have batch, 2 inputs, and we can then compute the output here. Oops, model batch. And then we can double check maybe the input. This should be 2 times 4, right? Oops, should be 2 times 4. 2 examples with 4 tokens. And then output should be 2 times 4 times the vocabulary size. So let's double check. So 2 times 4, and then each of the tokens is embedded in a 50,257 dimensional space. And we will take care of converting this in the next video. For now, I wanted to show you one more thing. So here I have this file, the dictionary that I defined at the beginning of this chapter, and I gave it this naming 124M, which stands for 124 million parameters. And so where does this number come from? We can actually calculate the number of parameters. And in PyTorch, there is a function or method called number of elements here, number of elements. So what we can do is we can compute, for example, the number of elements in batch. And this should be 8, right? We have 2 times 4 elements. So here, this is just like a convenient way to compute how many values are in a given tensor. So we can use that to sum over all the elements in the model. So for P in model parameters. So parameters are all the weight matrices, for example, and bias vectors that are in the model, all the trainable things that we have, basically. That's including the QKV matrices, but also the layer norm and everything. So yeah, and then we can print this out. Oh, I made a typo here. It should be null. And yeah, you can see it's a large number. To maybe show this a bit easier, let's use f string. Let's see if I get this right. F strings, if I don't use them in a while, I usually forget the syntax, but I think if I add a comma here, yeah. So we can see it's 163 million parameters that we have here. And so how does this number match with 124? I just told you we have 124 million parameters. And there's one thing I have not explained yet. So there is, in the original GPT model architecture, some weight sharing going on. So I told you before that this one maps from the vocabulary space into the embedding space. And then this one goes the other way around. It maps back from the embedding space into the vocabulary space. So what we can do is we can take a look at these weight matrices, right? So we could type model and then what is it? Token embedding. So let's take a look at the weight matrix and see how big it is. So we can see it's 50,257 times 768. And if we look at the output here, let me copy this one and then I will replace this with out head. This has exactly the same size. So one trick, because let's say we assume this is learning a good mapping. We're mapping from vocabulary space into embedding space, and we might assume that the same in reverse might work well. So mapping from embedding space to vocabulary space, so we could actually share the same weights. So we are not doing it here for simplicity, but we could technically reuse the same weights in the output head here. So because they have the same dimensions, and it's actually a design decision. Some people do that, some people don't. If you share the weights, yeah, you have fewer parameters in the model because these are really large matrices, but there are architectures or many architectures that don't do that. So it really depends. So Llama models by Meta AI, for example, Llama 3 and 3.1, they don't do the weight sharing, but 3.2 is doing the weight sharing. It's really, almost arbitrary. It depends if you want to save on parameters, you can share the weights, but otherwise, in my personal experience, it's not always leading to better results. So it's really like a trade-off between parameter size and better training dynamics, but it really depends on the architecture. But yeah, what I wanted to tell you is that the number of parameters here, how it's usually computed for GPT-2 models, because they usually originally used the weight sharing, is without counting it twice. So what I mean is here we count it once and we count it twice here. So sorry, let's focus on those here and here. If those are shared, we are overcounting. So what we could do is we could subtract, let's maybe do it here. We can subtract this one here. See if this works. So yeah, so you will get the 124 million that is usually quoted when people talk about GPT-2 models. I also have the paper open here. So here in this paper, this is the original GPT-2 paper. They should have a table somewhere. Let me see where they talk about the model sizes. Yeah, right here. So here they have 4 different model sizes, and this is the one we just implemented with the 12 layers and the 768 dimensional embeddings. You might notice this is not 124, and this is because they had a calculation error, I think. So I think they talked about it somewhere, I think maybe in the code repository, but they haven't updated the paper, which is why the number looks a bit off, but it should be 124 million. And they also have two different sizes here. And yeah, I'm maybe leaving this as an exercise for you, the viewer. So to implement those, actually, it should be relatively simple once you have the architecture coded. So you could copy and paste this here and then change some of the values here to make the architecture larger to implement the other ones you are seeing here in this table. I should tell you the table doesn't tell you the whole story. It talks about the number of layers and the embedding dimensions. So here the layers and the embedding dimension, where layers is maybe a bit unfortunate as the term, because this really refers to the number of times the transformer block is repeated. So it's used right here. So it's not necessarily other layers, it's really specific to the transformer block. So you could also maybe just call it number of transformer blocks to be more clear, or n blocks or something like that. But yeah, I'm sticking here with n layers because that's what's used in this paper and what's a convention nowadays in LLM terminology. But there's one more thing missing, and also the number of heads is different. So they didn't describe that in the paper, but you can see that actually when you download the model weights, and we will be doing that in chapter 5, that they also changed the number of heads. And for your convenience, I will just copy and paste these numbers here. So here I have the 4 different model sizes, GPT-2 small, which we just implemented, 12 layers, 12 heads, and 768 dimensions for the embeddings. And then medium, large, and XL correspond to these 3 models. And yeah, as an exercise, I encourage you to try out these models. You only have to change this vocabulary, so the dictionary here, and then you can reinitialize different sized models. And you can also compute the number of parameters, the size of the parameters, the number of the parameters and the size of the model using this code. And yeah, just find out how big these models are as an optional exercise. And then in the next video, I will go over how we convert the output back into words.
Get this book at Manning.com.